Problems on real numbers. First one, prove that root 2 is irrational. All of you know that root 2 is irrational because the root 2 value is 1.41 so on, non-terminating and non-recurring. But here we need to prove root 2 is irrational. Proof. So before going to prove root 2 is irrational, by contrary, to the contrary that I'm taking root 2 is irrational. By contrary, root 2 is rational. I'm saying that it is not irrational. Exactly opposite to that, I'm taking it is a rational. All of you know that if it is rational, it can be written as the form of p by q or some form p by q or a by b. Let root 2 equals to r by s, and think that suppose r and s have common factor other than 1, then we divide common factor to get root 2 equals to a by b, where a comma b are co-primes. Try to understand that. Just I'm taking it as a rational number. See, when you are taking the rational number, let it be 4 by 6. See here, 4 can be written as 2 into 2, 2 into 3. So 2 will get cancelled. That means 2 by 3. And here 2 and 3 are co-primes. That means I'm saying that it may be some rational number r by s. We may have r and s a common factor other than 1. So after dividing that common factor, you will get a by b, where a b are co-primes, like this. Now from this I can write b into root 2 equals to a. Squaring on both sides, I will get 2b square equals to a square. That means here I can write this as b square equals to a square by 2. That means 2 divides a square. From this I can write 2 divides a by theorem. If any prime number divides a square, it also divides a from the theorem itself. Now I'm writing a is equal to c, some other constant, a equal to c. Now it will becomes, equation 1 becomes 2b square equals to 2c whole square. Yes, obviously 2b, because in the place of a I'm writing 2 into some other constant c, because here a square is divided by 2 means, that means 2 is a factor of a. You can say that 2 is if 2 is dividing a square to get b square, that means you can say that a 2 divides a means 2 is a factor of a. That's why I'm writing 2 into something in the place of a, that equals to 4c square, 2 1s 2 2s. Now again b square equal to 2c square. From the second write b square by 2 equals to c square. Again here 2 divide b square, then 2 also divides b square according to theorem, according to b. That means 2 divides a, 2 divides b, means that is 2 is a common factor of a and b, which is false according to our statement, because we have taken a b a co-prime. That means completely false. Therefore what we have taken is wrong. So root 2 is irrational. Okay. Say that root 2 is irrational. Going for the next problem. Three plus 2 root 5 is irrational. No, same as previous problem. By contrary, 3 plus 2 root 5 equals to a by b. Root 2 by 5, root 2 into 5 equals to a by b minus 3. Root 5 equals to, so 2 root 5 equals to, take and I'm writing in the form of a where a comma b are co-primes. This is must and should. Again, take LCM 3b by b, then root 5 equals to a minus 3b by 2b. See here, you can see from this, therefore root 5 is to be rational. See, it is in the form of some rational form, p by q form. Rational according to our condition, which is false, because root 5 is irrational. You know that root 5 is irrational, which is false. Therefore 3 plus root 2 5 is not rational, is irrational. And for the next problem, 3 root 2 is irrational. Solution. By contrary, root 3 is rational. If it is rational, it should be in the form of a by b. Root 3 equals to a by b. A comma b are co-primes. From this, root 2 equals to a by 3b. a by 3b. From this you can say that a by 3b is rational. That implies root 2 is rational, but which is false? Which is false, because we know that root 2 is irrational. Therefore 3 into root 2 is also irrational. Hence prove. Show that any positive odd integer is of the form 6 cube plus 1 or 6 cube plus 3 or 6 cube plus 5, where q is some integer. Solution. So we need to prove that any positive odd integers in the form of 6q plus 1, 6q plus 3 or 6q plus 5. Let's take a equal to bq plus r Euclid division lemma. Now compare with this. Now a equals to 6q plus r. That means here b is 6. Now r should be less than or equal to 0 and greater than or equal to 0 and less than 6. That means the values of r 0, 1, 2, 3, 4, 5. Then we will get the values 6q, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 5. Now if you change the value of q at q equals to 0, he'll get 6 into 0. Directly you can write 0, 6 into 0, 0 plus 1, 1, 2, 3, 4, 5. At q equals to 1, you'll get 6, 7, 8, 9, 10. That means on changing the values of q, you'll get all whole numbers, all positive integers with along with 0. But we need only odd integers. Now from this, 6q can be written as 2 into 3q. 6q plus 1 can be written as 2 into 3q plus 1. That means this is something 2 into 3q. So 2 into some constant a or some constant x. Here 2x plus 1. 6q plus 2. If I take 2 common, we'll get 3q plus 1. Means again in the form of some x, 2x. 6q plus 3 equals to 2 into 3q plus 1. Again plus 1 remains because 2 3 6q. 2 ones 2 plus 1 gives 3. Means again 2x plus 1. 6q plus, here we missed one thing, 6q plus 4 also. 2 into 3q plus 2, that again in the form of 2 into something, 2 into x. At last 6q plus 5, that equals to 2 into 3q plus 2 plus 1, because 2 3 are 6q, 2 2 are 4, and remaining 1 gives 5. So again this is in the form of 2x plus. All of you know the numbers which is in the form of 2 into something are even numbers, and even 2x plus 1 are odd numbers, because even plus 1 gives odd number. Therefore 6q plus 1 comma 6q plus 3 comma 6q plus 5 are representing any positive odd integer where this condition important, where q is some integer. So we have to change the q value of q, then you can get all the numbers sequentially on if you take q sequentially. So among them we have to pick the odd numbers, which are 6q plus 1, 6q plus 3, and 6q plus 5. Next question. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer. Yep. Solution. Let all positive integers are in the form 3q 3q, 3q plus 1 or 3q plus 2. See, what he asking to prove is using division lemma. Square of any positive integer should be in the form of 3m or 3m plus 1. That means 1 square, 2 square, 3 square. Any positive integer square should be in the form of this one. So now I am taking all positive integers in the form of 3q, 3q plus 1, 3q, because we cannot prove for everything 1, 2, 3 up to infinity. Now we are summarizing the all positive integers in the form of 3q, 3q plus 1. 3q. I will explain it. Say 3q. For q equals to 0, 3q means 0, 0 plus 1, 1, 2. At q equals to 1, 3, 4, 5, so on varying the q values, you will get all the positive numbers, positive integers. That means it is enough to prove that 3q square, 3q plus 1 whole square, 3q plus 2 whole square are in the form of 3m or 3m plus 1. That obviously we have proved the square of any positive integer is in the form of this. So I am proving 3q square. First of all, 3q whole square, that means 9q square. Again I can write this as 3 into 3q square. Yes, let it be m, so 3m. Second one, 3q plus 1 whole square, 9q square plus 6q plus 1. Again I am taking 3 common here, then you will get 3q square plus 2q. In among this I took 3 common, so plus 1. So again it will be m, so 3m plus 1. Third condition, 3q plus 2 whole square, that means 9q square plus 2 2s are 4, 4 3s are 12, 12q plus 2 square 4, a square plus 2ab plus b square. Now again I can write this as 9q square plus 12q plus 3 plus 1. Among this I am taking 3 common. If I take 3 common, 3q square plus 4q plus 1 and again plus 1. I am taking this as constant m, so 3m plus 1. 3m plus 1, 3m plus 1. That means if you take square of any positive integer, it should be in the form of, they should be in the form of 3m or 3m plus 1. Next sum. Use Euclid's division lemma to show that the cube of any positive integer, the cube of any positive integer is of the form 9m comma 9m plus 1 or 9m plus 8. He is asking to prove that if you cube any positive integer, it should be in the form of 9m plus 1, 9m. That means 1 cube, 2 cube, 3 cube, 4 cube, so on. Any cube, any positive integer cube should be in the form of 9m plus 1 or 9m plus 8. For that I am taking, let all positive integers are in the form of 3q plus 1, 3q plus 2. I am taking common form for all positive integers, 3q plus 1, 3q plus 2, as I said in the before sum. Now first one, 3q whole cube means 27q cube. If I take 9 common, I can write this as 9 into 3 q cube. Yes, it is form of m, 9m. Second one, 3q plus 1 whole cube, that means a cube plus b cube, a cube plus b cube plus 3ab into a plus b. That means 27q plus 1 plus 9q square plus 3q. So 3 into 3ab, no? 3 into 3ab. So it is in the form of a plus b whole cube, a cube plus b cube plus 3 into ab into a plus b. So 3 3s are 9q, 27q square, 3 into 3 9, 9q, 9 into 3 27q square plus 9q. If we observe this, in these three terms I can take 9 common, yes. Take 9 common, we left here 3q cube plus here 3q square plus here q, and at last plus 1. I'm taking this as constant m, so I can write this as 9m plus 1. Last one 3q plus 2, 3q plus 2. Whole cube. Again a cube plus b cube plus 3 into 3q into 3q plus 2, so into 2 into, because 3 into ab into a plus b. This means 27 9q plus 8 plus 3 3s are 9, 18, 18 3s are 54q square plus 2s are 4, 4 9s are 36q. Again from these terms I can take 9 common, 3q cube, 9 6 are 54, 9 6 q square plus 9 4 36 4q plus again I'm taking this as a constant m, 9m plus 8. Now if you observe that cube of any, because this 3q plus 1 3q plus 2 represents all positive numbers for all positive integers, so cube of all positive integers must be in the form of 9m, 9m plus 1 and 9m plus 8. Consider the numbers 4 power n where n is a natural number check whether there is any value of n for which 4 power n ends with the digit 0. Now he's asking that consider 4 power n, n is a natural number. That means for any value of n, will 4 power n ends with digit 0. That means 4 power n should be multiple of 10. Say 4 power 1, 4 square 16, 4 cube 64. If you change the value of n for any other value, let it be multiple of 10 or not, whether it be multiple of 10 or not, for that. So if the number 4 power n were to end with 0, for any value of n, it would be divisible by 5. That means 4 power n should contain prime factor 5 or prime factor prime. But 4 power n can be written as 2 square whole power n. That means 2 to the power of 2 power n. That means only prime in the prime factorization of 4 power n is 2. Therefore 4 power n does not end with 0 for any value of n. Going for the next question. Check whether six power n can and with the digit 0 for any natural number n. If 6 power n would end with 0 for any value of n, prime factorization of 6 power n should contain 5. Since number ended with 0 must be divisible by 5. That means if any of the number for any value of n, 6 power n end with 0 means it should be divisible by 5, because the number ending with 0 should be divisible by 5. That means if it is going to divisible by 5, 6 power n should contain the factor 5 in prime factorization. Now let's go with the prime factorization of 6 power n. I can write 3 into 2 whole power n. That means 2 power n into 3 power n. Therefore prime factorization of 6 power n contains only 2 and 3, not 5. Therefore 6 power n cannot be ended with 0 for any value of any natural number n. Going for the next question. Explain why 7 into 11 into 13 plus 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 1 are composite numbers. Take first one. 7 into 11 into 13 plus 13. Take 13 common. We left with 7 into 11 plus 1, because 13 here taken common, means 13 into 77 plus 1, which gives 13 into 78. That means 13 is a factor of given expression. That means if anything will be factor of a given number, this is like solve it to get number or expression, it is factor, then this not be a prime number, it must be a that is 7 into 11 into 13 plus 13 is not a prime, it means is a composite number, it will be a composite number. Now go for next one. 7 into 6 into 5 into 4 into 3 plus 5 now. 3 into 2 into 1 plus 5. I'm taking 5 common here. We left with 7 into 6 into 4 into 3 into 2 plus 1. It means 5 into something, some number. Here 5 is a factor of, let it be number, not expression, because there is no variable. Given number. That means if we have factor other than 1 for any number, it is a composite number, not a prime number. Therefore 7 into 6 into 5 into 4 into 3 into 2 to 1 plus 5 is a composite number, is a composite number.